2, 1. All right, so let's dive in. So motion equations. In one of the earlier chapters in Foundation of Physics, you're going to run into quite a lot of formulas. And in these particular formulas, you are going to have to be solving for some unknown. So you're going to have to be acquainted how to manipulate these formulas a little bit. Most students coming into physics, they have either forgotten, how to solve for unknowns, or it has been far enough removed that they do need a little bit of refreshing. So I want to do some of that refreshing in this particular video. So I want to take in a formula, take some givens which are provided to us, and then be able to manipulate the formula to solve for whatever it is that we are interested in. And I'll give you some tips, what to think about in these particular chapters. All right, so let's start with the first example. There's actually quite a few examples in this video. So the first formula that we have is this formula, which is nothing else but the average velocity. And typically this is when your acceleration is equal to 0. And this formula you use by taking the change in your position, and then it's divided by the change in time. So let's take a look and see what possibly could be given and what you would have to actually do. So the first thing is, so this is for part A that we have in here. It states that we have a change of displacement, and it is 14 kilometers south. And then we have a change in time and 30 minutes. Now we want to be able to find for us, what this, actual average is. So notice we have this and we have this. So basically we can substitute these back in here and we are going to be able to find out what our average is. So here's the first thing to be aware of. You do need consistency of two actually things which you don't normally think about when you're substituting it back into formulas. So remember that these particular formulas typically do assume that you have consistent units, and you have to pick whatever units it is that you want. So you have to kind of look at what are they asking me for. And what I mean here is, sure, they want me to find this, but they want me to find this in kilometers per hour. So we need to have our displacement in kilometers. So we have to check that. So yep, that's fine. And we need our change in time. So in this case, notice that it's in hours. Well, this is not what we have over here. So that's the first kind of item that I would worry about. I would say, okay, well, 30 minutes, I have to change back to hours. That's not very difficult, and most students will know that 30 minutes is nothing else but simply half an hour. All right, so this is what we have, so I'm going to just change that. So that takes care of the first item that all students should be aware of. What units do you exactly want? If the units are not listed for you, then you typically assume that they're standard SI units. And for that, if you are thinking about standard SI units, well, the displacement would be in meters, and then your time would be in seconds, if that's not listed. For us, it is listed, so we'll follow what they're asking us for. Now, here's the other thing that you have to be aware of. The direction, right? So because you are dealing, with some of the actual quantities as vectors, then you have to be aware of, what direction are they seeking, and does it align, with what we have? So in this case, notice this is south, and we want it as south as well. So this is all consistent as well. So check mark over there. The time has no direction because it's simply a scalar. So now that we've identified that, we can go ahead, and do this particular question. So this is for part A. So we are going to have our average velocity is equal to, so notice this is going to be 14 kilometers, south, divided by, and this is going to be your change in time, which for us is just half an hour. And we have our kilometers per hour, and then we have our actual direction as well. So there you have it. So 14 divided by 0.5 is actually 28. You can certainly look that up for yourself, on the calculator if you're uncertain. And then we have to, stick with the actual directions. If, you are not given a direction, then you just assume that the direction with respect to the reference, is going to be positive as it is. But in this case, we do have the directions provided. Okay, so now that I have this, now the third kind of check for ourselves is make sure that we round correctly. So sometimes they'll tell you what to round to, and that might be, round to 1 decimal place, or maybe the 10th, the 100th. So you should be comfortable in rounding, right? I'll put up a link up above there to just the standard rounding. The other way of rounding, especially in physics, is going to be with regards to significant figures, because they capture measurements for us. And this is exactly what happens here. So here they say, okay, so round to 2 sig figs. Well, I have 1 2 sig figs, so I don't have to do any further rounding. It's already to 2 significant figures. That's the answer. You want a review on rounding to significant figures? I'll put up a link up above there where it captures a few examples for you. All right, so that's part number A. So now part B. All right, so let's take a look and then go through our checklist of the things that we should be looking out for. So now they actually give us what the average is, and this is going to be the first dive into manipulating this formula. So notice we have this. Okay, now we also have been given, okay, so this is the displacement, and we're supposed to find the change in time in seconds. All right, so let's see if you remember. So what should we be looking out for? Well, we need to figure out units, right? So units have to be consistent. Now, looking at the answer, because we have time, so this has to be in seconds, right? So that means I'm going to go back. Well, this is actually both in seconds, so that's all good. The displacement, however, notice it's in kilometers right here. Time, I have no kilometers, but I do have, okay, the units right here. So notice this one is meter, this one is kilometer. Are they consistent? No. So you have to make them consistent. Now, because we're just worrying about time, then it doesn't matter which one you pick, meters or kilometers. But it's probably easier to, if it's not necessarily stated, just to go with SI units. So what I'm going to do is I'm going to change this. So this right here, the 1.5 kilometers, there's 1,000 meters in a kilometer, right? So this is going to be 1,500 meters. All right, so that is my actual measurement value. So I have my displacement now, and it aligns with my actual velocity. So this is all consistent that I have there. Now, what else do we need consistent? We need the direction to be consistent. Well, time on its own, there is no direction because it's a scalar. So we have to move back up to the other ones. Notice this one is west, right? And this one is west. Well, they are, okay, in the same direction. So that means we can use the formula as it is. We don't have to change any of the directions. So the directions are consistent. All right. So now, plugging it back into the formula. So as you're kind of going in, well, so I'm going to have, okay, so this is 10 meters per second. Because all my units are consistent, I can drop them now. I've kept them within here, but once you make them consistent, you don't necessarily have to, right? You'll just know what your answer is. So here, this is going to be 10. Maybe I'll put them in here, okay, just for completeness. This is going to be meters per second. Do you have to put in, okay, your directions? You do not, right? Once you make all of them, say west in this case, you don't have to necessarily put them in. Now, the displacement on its own, so this one is going to be 1,500 meters. And this, okay, is going to be what we're trying to solve for, which is going to be delta t. Now, to get delta t, okay, right here, so we can move this right here and we can bring it up, okay, over here by multiplying both sides by delta t, right? So delta t will cancel, okay, and it's going to appear over here. And what we will have is we're going to have, 10 meters per second, and this is going to be times delta t, and this is going to be 1,500 meters. Now, dividing both sides by the 10 meters per second, right there, so that gets rid of this, and it just leaves me with delta t remaining there. All right, so now notice, okay, so it's going to be 1,500 divided by 10, which is 150. Again, you can check on a calculator if needs so be, and it is just seconds, right? So this actually, if the meters per seconds were left here, the meters will cancel, the seconds would come up on top, and then I have the unit that I wanted. And now finally just check your rounding. Now here it says 2 significant figures right there. So if I take a look at this, well, it has actually 2 significant figures right there. So I'm going to leave it as it is. So that's question number 1, and then manipulation of it. So the key things is we want consistency, both in units for the formula, and 2, we want consistency in terms of your direction. So be careful of those 2 items. All right, so that's page 1 done. Here's page 2. So here's another example, different formula, however. So this is another kinematics formula. So this is one with regards to motion. This one looks like we have some average, some constant uniform acceleration in here. So we'll see what we have to do. Okay, so let's give it a shot. So what do we have? Well, we have V final. So notice that's the vector there. We have V initial. Okay, that's the vector over here. And then we have time given, and that's the scalar in this case, okay, given at the end there. And that's my formula. So with this formula, I have to substitute all of this back in here. Now, let's check the units, right, in terms of consistency in here. Okay, so let's take a look. I'm going to take a look and see what they're asking me for. So they're asking me to find the average. Okay, they want it in the west direction, right? But they're not giving me any unit. So this is the case where if they don't give you any units, you assume that it is going to be your metric, okay, SI unit. So your kind of base unit, which is meters per second squared. So that is something that I'm going to assume because they don't give me anything else to work with. So if that's the case, then I'm going to go back and I'm going to take a look and see. Well, for my velocities, my 2 velocities, notice they're both in meters per second. So that's all good. My time is in seconds. So that's also good because that means everything is consistent in terms of seconds, okay, that I'm going to be working with. So nothing to do on that front. My direction, however, because they want me to keep my direction west, which this one is west, but this one is east. So, what do you know about vectors? Well, for vectors, if you're going to switch the direction from, going east in this way, if you switch it back to west, what happens? The sign will change. So this really is just simply 25 meters per second west. That's the same exact measurement. Now I have consistency in my west direction, which is exactly what my answer should be. So once you have that taken care of, now you can take a look, right? You can take your formula or your equation in here. I'm going to duplicate it and bring it back down here. And I'm going to substitute all the values that I have right above. So VF, so in this case, is going to be 25. I'm going to this time around not actually write the units, right? Okay, because they're all consistent in the formula for my velocities and time. And my direction I'm also going to drop because indeed they're all west, that I've changed it. My VI, so this is going to be 2 plus, now this is my acceleration that I'm looking for, and it's going to be multiplied by time. Now that time I'm going to put that 12 and I'm going to swap these. All right, so this is what I'm going to write in. So it's the same thing. If you put it in the back or in the front, they're just multiplying each other. And now I can solve. So here, solving this out, I'm going to bring this on the other side. So this is 25 minus 2. It's going to leave me with 12 and acceleration, okay, that I have in there. So that's 23 is equal to 12 times the acceleration. Now divide both sides by 12. This is division by 12. And then I'm going to get whatever my average is. Now on that last line, I'm going to put back the units, right? Just to make it all kind of seem what it's needed. Now, I do want 2 significant figures. Now, by the way, it's not always 2, okay? It might be something different. So just watch out what your teachers want from you. So I'm going to actually take out a calculator here. So 23 divided by 12. So there you have it. Now rounding this to 2 significant figures. Okay, so in here, so this is what I'm going to do. So that's going to be equal to, so approximately Now you can write more digits. I'm going to right away round this. So that's 2 sig figs that I have. And if I put in here the unit itself, which you should, if your teachers are expecting you to do this, do it in the right way. So here's your unit, and then there's your direction, and there you go. So it's a constant acceleration of approximately 1.9 meters per second squared. So what does that mean for us? Well, in this case, if you understand acceleration, it would mean that you're actually kind of, because you're heading, okay, in the west direction, it looks like you're going to be speeding up. Okay, so, and that certainly is the case during that duration, because notice that your initial velocity was only 2 and your final was 25. So clearly you've sped up during that 12-second time span. So there you go. That is it. That's all that you would have for this example. Okay, so let's keep chugging along in here. So here's the following example, okay, to this. It looks like a different formula once again. So let's take a look and let's see what they are looking for. So my formula right here, so this is what I'm going to be using. They give me what the displacement is, so I will know that. Notice it's in kilometers, north. They give me my initial velocity. This one is in meters per second, so I already know that I have inconsistent units. And then my time is in minutes. Okay, even worse. Okay, so this is also not consistent at all. So now, if I'm looking at this, so this is what they want me to find, which is my final velocity. They want it in kilometers per hour, and they want it north. So for consistency, so I'm going to need kilometers and I'm going to need hours, all right? And I'm going to need a direction of north. So the first one, kilometer, that's good. North, that's also good. Meters per second, not good, because I need, if I want, okay, I'm going to have to change this back into kilometers per hour, because meters and seconds don't align. And then this one is north. Okay, so I'm going to have to change this. Now, in order to change this, I need, unit conversions in here. Well, first of all, so the, meters and kilometers, okay, that you have, so you should remember, so there's 1,000 meters, okay, in 1 kilometer. So that would change and get rid of, okay, that meter for me, and it would change this to kilometers. Now, the seconds that I have, so you can do it one of two ways, okay? So we know that there are 60 seconds in 1 minute, and, okay, so we have, this is going to be 60 minutes, okay, in 1 hour. And now this is the conversion that you would have to do. Now notice the seconds will cancel with seconds, the minutes will cancel with minutes, okay? And now you can compute what this exactly is. Now, it turns out if you ever do go from meters per second to kilometers per hour, okay, you'll notice that the conversion, so if you actually multiplied all of this in, it's going to give you 3.6, right? Because 60 times 60 is 3,600, and then divided by 1,000 is 3.6. So that entire piece, and this is, if you really want to have a good memory, you can keep this, that this is going to be 3.6, and it's going to change it back. So if you're ever going from meters per second to kilometers per hour, you can multiply by 3.6, or you can do the conversion that I have just done. So either or, okay, will work well. So what does that tell us? Well, so all of this work that I have done, okay, so this entire piece, I'm going to make it smaller just so that I have room to write this out. So this, so 10 times 3.6 is, 36 kilometers per hour. So now I have it in the consistent units that I wanted. The last piece, so this one is also annoying because I have it in minutes. Well, I don't want to have it in minutes. So I'm going to get rid of the minutes. So that's going to get rid of that. So 60 minutes, well, it's equal to 1 hour. So it's going to be 12 over 60, right? So if we don't remember, okay, so 12 over 60, which is going to be 0.2. So this is 0.2 hours. So it's a lot of work before beginning, right? But that's what you need. You need to always think about what units am I going to be working with. If your teachers, your textbooks, whatever it is that you're using are kind to you, they'll typically will keep everything in meters per second. The problem with that is you're going to get so used to thinking that everything is in meters and in seconds that when it does change, you're going to get thrown back and you'll be like, oh, what do I do now? So that's why I like doing, this style of a video where I'm really testing you on everything, unit conversions, plugging things in, and knowing what to keep in mind, okay, as you're substituting things into formula. So the units have to be consistent and the direction has to be consistent. So notice it's all north, all right? If there's no direction at all for anything, then you just assume they're all in the same direction, but they just haven't given you that information, okay? So now let's substitute all of this back in here. So if this is my formula, right here, so I'm going to steal this formula in here and duplicate it and bring it back down here. So if I start substituting all of this stuff in here, so this is going to be 2.5, right? So it's all in kilometers and it's north, so I'm not going to put any other piece of information there. The next set of information, so VI, well, so that's 36 plus, VF. I don't know what that is. Going to be divided by 2, and then the total time is 0.2. All right, and that's an hour, so everything is nicely consistent. So we have to solve for this, right? So I have to be able to solve for this. So what do I do in this particular case, right? So, well, there's many ways of being able to see what needs to be done. So I have, okay, as I start this off and try to solve through this, I certainly don't want to have this 0.2 and I don't want any denominators. Now, the denominator is simple, right? You can multiply both sides by 2 very quickly and that denominator will be gone. So this is going to give you just 5 on the left-hand side and then you're going to have 36 plus, your VF, okay, on the right-hand side times 0.2. Now you have an option. You can bring this inside of the brackets, or you can divide by 0.2 on both sides. So both will work just fine. So that I leave up to you, okay, whatever it is that you want. So maybe I'll just bring it inside of the brackets. So 36 times 0.2, I guess it's going to be 7.2 plus, 0.2 is going to be VF. And then we have our 5 on the other side, all right? Again, you can use your calculator if you want to just kind of double check for yourself. So 0.2 times, 36 indeed is 7.2. So now I'm going to bring this over to the other side. So 5 minus, and this is 0.2, VF. So that's all good. This becomes negative 2.2 and equals to 0.2. This is VF right there. All right, so this is what I have. Now dividing both sides by 0.2. So this divided, so that's gone. This gives me VF as a vector. Notice it's going to be negative, right? So 2.2 divided by 0.2. So that's what we have there. So this is 11, right? Now, please keep in mind, because now we have to bring back the units. So this was in kilometers per hour, and the direction, okay, was north, right? So we kept everything north. Now it is negative, right? So it's negative. So what does that mean for us in terms of this velocity? So really this negative, right, and this being north, right? So if north is going in this direction, okay, if that's up north, then this is really saying that it is 11 kilometers per hour south, right? So that's what this would be, because the negative would change the direction, okay, of your vector. So either or is fine, but they want the answer to be on the north side, so that's why we kept all of those. So I'm going to remove this one and just keep that answer as it is. And I guess for significant figures, it's still 2. So this is actually 2 sig figs in there. So 1, 2. So that's your answer. And there you have it. So you've substituted it back in and you've manipulated your formula or your equation. Here is another example, right? So as you're kind of chugging along, I'm giving you as many examples as I can, right? So that you can, again, think about it. These examples and the formulas are getting a little bit harder and harder as you're going through. So here I have two pieces. So I think I'm probably going to need an extra page here. So I'm going to add it up there for space. Okay, so let's look at part number A. So for part A, so what do we have given? We have our initial velocity. We have our change in time, so that's that. And it appears in two places there. And then I have my, okay, kind of average, so this is that. And now I'm going to need, okay, my displacement, all right? So, well, let's check. So units, okay, this one is in meters per second, all right? So that's fine. This one is in seconds. This one is in meters per second squared. So everything is meters and seconds, right? So that's what I want. They want it in meters, so that aligns perfectly. But now direction. They want the direction to be east. So this one is fine. Obviously, there's no direction for time. It's a scalar. But this one is not fine because it's west. So I have to change this back, put it negative 1.5 meters per second squared. And now I have to change this to east. And notice that this negative takes advantage of these. These are equivalent to each other in terms of your vectors, right? So just the way that we write a vector. Okay, so that means it's in the opposite direction. Okay, so if you're moving at 3.8 meters per second, then now it's going to be negative. Okay, so those don't align, so that means you're going to be slowing down in some way. So let's take a look at, what this will actually yield for us. All right, and then we can think about what the meaning of it is. So let's substitute it all in. This is going to be my equation to work with. So let's copy this. I'm going to bring it down. Okay, so within here, so this is, let me maybe change it to the color that I'm using. Okay, so this is for part number A. All right, okay, so now let's substitute it in. Luckily, we don't have to do anything because we are actually solving for this. So that means we just have to evaluate this by using our regular order of operations in here. So that is now, okay, so my VI, so that's going to be 3.8. I drop all the units because of the fact that they are consistent. My time, so my change in time was 8.8, so that's 8.8 plus 1/2. Okay, now my acceleration, this is where I have to be careful, it's negative 1.5. And my time, which is 8.8, and notice it's squared. So this is all I have now. So I know that my answer, okay, because of the fact that I used meters and seconds, my answer is going to be in meters, and my direction is going to be east, okay, for this. So, well, let's write it all out. So this is going to be, so 3.8 multiplied by 8.8, all right? So you can write this in here, right? So you can put that in there. You don't have to. You can do it all in one step, right? So it just depends how good you are with your calculators. I'm going to write it in just so that you have a reference point for this. Now notice that negative is going to come out in front, so I'll just leave it there. So this is going to be 1/2 is 0.5, so 0.5 times 1.5 times 8.8, and this is squared. All right, so that's what I have there. And that's going to be 58.08. Now, at this point, you might ask, what about rounding? So they're saying, still sticking to two significant figures. Unless your teachers tell you otherwise, in intermediate steps, so these are two intermediate steps, we have an intermediate means it's not the final answer. Don't round anything. So like, don't put these to two significant figures and then do the addition. There are some rules for that, but typically in foundational physics and most sciences, in the intermediate steps, you'll just keep the decimals as they are. And then once you compute and you get to the final answer, so now that we will get to the final answer, only then, round to whatever it is that they want you to round. So this is 58.08, and this will give us negative 24.64. So notice this is meters, and it is in the east direction. So I have that. And now I will round this, so approximately. So they want two significant figures, so this is going to be negative 25 meters east. And there you have it. That's how you would leave your answer. Now, negative 25 east, like don't think that you went negative 25. It means that, you were going kind of, so in this case, what you ended up with was really 25 meters west, right? With respect to the reference point. So that's what it would mean. You started off at east, and then because of the fact that you were decelerating, okay, and then you were just started to go in the opposite direction. So that's all that it means, right? So the negative, don't let that throw you off, right? Because it just means that now it will be in the west direction. All right, so that's part A. Part B. So let's take a look at part B over here. Maybe I'll switch the colors and let me steal, okay, this thing. And I'm going to put it on the other side here. So let me put it as a fresh start. And so for that, we also are going to need our formula or equation. So I'm going to duplicate this, okay, and bring it back down for ourselves again. All right, so let's see this. Again, we want all consistency. So first, let's check out what they are looking for. So find your acceleration. So this is going to be a little annoying because we're going to have to manipulate our formula or our equation. We are given our displacement, okay, so that's our displacement right there. I guess it is missing a little vector, okay, symbol there. So we have our displacement, 150 meters, that's north. We have our initial velocity, so that's 2.5 meters per second. This one, notice it's south, okay, and then time is 25 seconds. So they do want this in meters per second squared. So we want everything in meters and seconds. So meters, seconds, okay, so everything is fine on the consistency of units. On the direction, we want north. Okay, so well, this one is fine, but this one is not. So what that means is we have to change this. So this is going to be negative 2.5, meters per second. And this is north, right? So it's opposite. Notice the sign has changed now. So I've just swapped it. So now it's consistent direction as well. Let's substitute everything back in. So let's see. So 150 equals. So now it's, now be careful in here. It is negative 2.5 because we switched it, times 25 plus 1/2. This I'm going to bring to the back, right? So you can do that because it's a variable that I have in there. And then the time, which is 25 squared. Okay, so that's how I'm going to rewrite this. Okay, so there you go. And now let's compute all of these. So this is 150. And now let's see what this gives me. 2.5 times 25. So that's 62.5. That's negative still. And this one, which is going to be 1/2 times 25 squared. That's going to be plus 312.5. All right, so there you go. Now let's shift things around. Let's bring this over to the other side. 150 plus 62.5. It's going to be 312.5. And the acceleration. All right. Okay, so what does this give me? I guess this is going to be what? 212.5. And so finally, dividing both sides by 312.5. There we have it. So that's gone. And this leaves us with what we wanted. All right, so let's take a look at and see what this will give us. So 212.5 divided by 312.5. Okay, so this is 0.68. Notice I didn't round anything before, okay, and this actually worked out relatively well for us in terms of number. 2 sig figs, well, this is actually 2 significant figures, 1 and 2. So I guess the only thing is we have to bring back our units. So in here, you can bring it back or put a concluding statement. This will be in meters per second squared, and this was north. All right, so there you have it. So that's what this would be. So that's another example. It's a nice example because it shows you how to manipulate the formulas themselves. Okay, so here's a last one for you. Okay, so a little bit of a torturous set of examples, but hopefully useful, that you are comfortable in doing these things. So here's my last piece. So here's what we would have. Let me copy this, paste it down. And so for this example, okay, so what do I have? They give me the velocity, right? Notice that it is vectors. Now for this formula, notice that there's no vectors in the formula, right? So these are not vectors. Now the reason for that is because in this formula you're squaring, and you can't really square a vector directly. So really this just talks about magnitudes that you have, but still keep things consistent, right? So still keep your units and directions consistent. But when you're plugging in, you know, your answer is actually not really going to, you know, be anything related necessarily towards, okay, your direction for your, in this case, for your initial velocity, right? So let's take a look. Let's substitute this back in here and let's see what happens. So first of all, in terms of units, notice meters per second squared, meters. And this one says find, you know, your initial velocity in meters per second. So everything actually lines up pretty well. Our directions, okay, that we have, they're all actually east, right? So this is what we have in here. Okay, so that's good. And then, you know, so the assumption is that this one is actually also going to be east as well. Okay, so let's take a look. Now substituted it back in there. So VF is going to be 10.2, but it's squared. VI is what I'm supposed to find. So it's going to be, I'm going to leave that as it is. It's going to be 2 multiplied by the acceleration, which is -1. And then your displacement was 85. Okay, so this is what I have in there. Let's try it. This is going to be negative because of that. So 2 times 1 and then 2 times 85, right? So 2 times 1 is 2, and 2 times 85, which is 170. That's what I will have over here. And now finally, so the 10.2 squared. Okay, I'm going to just square that, which is going to give me 104.04. Again, I'm not rounding in here just yet. We'll round the final answer. Okay, so in here, and actually they don't specify, so that's fine. Okay, in terms of rounding, so we'll see what happens. So this is going to be 104 minus, okay, so it's going to switch its sign, so it's plus 170 VI squared. So I have my answer plus 170 equals, so this is going to be 274.04. And now what do you do when it's squared? Well, you're going to have to take the square root of both sides. So that means that VI is the square root of all of this. Now, when you're taking the square root, the answer can be either positive or negative, right? Because of the fact that when you're squaring, okay, you know, when you square something, if you square a negative, it's still going to give you a positive back. So that's why the answer is either positive or negative. We typically will take the positive answer in here. So the square root, okay, this is going to be of 274.04. And that is going to be, you know, plus minus, so 16.554, etc. Okay, so now since they didn't specify for us, in here, what to round to, then typically what we will round to is the smallest number of significant figures that I had in the measurements. So in this measurement, I had 1, 2, 3 sig figs. In this measurement, I had only 2 sig figs. And in this one, I also have 2. So 2 is the minimum. So I'll just kind of round this to 2 significant figures right there. So that would have been actually 17 meters per second. And, you know, we'll take the positive side, okay? So within there, and that would have meant that we are going on the east, okay, direction, okay, in here. But if you're just substituting things back in and you don't have any other pieces of information, this is as good as it can get. So that is your initial velocity that you were moving at. So it went from 17, okay, and then it got itself up to, okay, 10.2, right? So notice that if you were moving east, so what this would look like is, you know, if you're moving in the east direction, you know, you started off, and this was, you know, you started off at 17 approximately meters per second, right? You're moving in the east direction. Notice that you are, okay, after a while, you've gotten yourself to 10.2 meters per second, still east, okay, direction. So visually, you can have that. But notice what's happening to your speed. It is slowing down. And what would that mean? That means that we should have a negative acceleration, which we do, right, in that direction. So it is actually slowing it down. And in that process, you still moved 85 meters. So that's what this would mean, okay, as you're going through here. So it actually forces you to also understand, okay, on the direction side, what is happening. So there you have it, okay? So that would complete all of the examples, and the goal was to try to get you to understand consistency, make sure your directions are aligned, and then making sure that you can still substitute and then isolate for whatever it is that you need. So you need a little bit of a background in solving for unknowns. All right, thanks for watching. Okay, welcome to physics. Bye, everybody.